Alright guys, so today you're going to be looking at a pretty familiar situation. So we've got a cart that is being pulled by a hanging mass across this pulley down this straight track. And what we're going to hope to do is check the work kinetic energy theorem, So the idea here is that this hanging mass is doing work on this cart, and the amount of work it does should be equal to the change in kinetic energy. Very simple. And so what we're going to do is I'm going to show you how to take a sample set of data that we collected in class today and extract some information from it, use that information to check whether the work done on this mass is equal to its change in kinetic energy. Then we'll do it a second way where we actually look at the work done by the hanging mass and check if that's equal to the change in kinetic energy of our cart mass. Okay, so here it is again, the first method we're going to watch the work done on the cart and see if it's equal to the change in kinetic energy. So before we get into the data, a little bit of the theory. So you guys already took notes on how work is equal to the change in kinetic energy. You saw that using a little bit of calculus, but we're going to try to apply it here. So first of all, you know that the work is the force times distance, and here the force is in the same direction as the displacement of the cart, and so we know that it's okay to use just the straight up force that we'll calculate. No angles involved or anything crazy like that. On the other side, we know that the change in kinetic energy is just going to be the difference between the final kinetic and the initial kinetic energies. And since we let the cart go from rest, we know that the initial kinetic energy is going to, of course, be 0. Our next move is that we're going to expand out the left-hand side. So we know that force equals ma, Newton's second law. Now here we're going to be talking specifically about the mass of the cart times its acceleration. Later we'll look at the mass of the hanger. So we'll multiply that by distance. That left-hand side is just work still, force times distance, of course. And then on the right-hand side we'll have 1/2 m times of the cart mass, so the mass of the cart, times the speed squared. So what we'll do is we'll find each of these data. We'll find the acceleration, the distance, and the speed from the program graphical analysis, which you should have on your iPad. So I will link on Schoology this set of data. You'll just download it and open it up in the app, which should be pretty straightforward. And the other information that you'll need before we get into what the data looks like is you'll need to know that the mass of the cart is 1.58 kilograms. Okay? So anyway, here is a sample of the data, what it should look like. You'll notice that on the top we have distance versus time graph, and on the bottom we have a velocity versus time graph. I want to draw your attention to just right of where I have the cursor in the program, right here. And what you'll notice is that at that moment the velocity drops pretty sharply and then steadily decreases. This is the moment right at the top of that peak when I stopped the cart, or the person in the video stopped the cart, and it started to slow down from there. The reason the velocity is still positive is because the pulley is still spinning, so the program thinks that the cart's still moving, but really it's just the pulley continues to move. That's why the displacement continues to increase after the cart is completely stopped. So what we'll do is we'll use the data tables in here to find distances, speeds, and accelerations. And I'll show you how to do that right now. So you can switch the option to graph and table, and keep in mind you'll be doing this on your own in a second. And what you'll notice is I've toggled over, I picked any random time, and when you'll do this, you'll pick some other time besides 2.63 blah 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 seconds. So anyway, I picked that, and in the data table it shows me that at that time the distance was, as you can see, 0.656 meters. The velocity was 0.832 meters per second, and the acceleration and force, we don't really care about those right now. And so anyway, we will take that information, both the distance and velocity, and we'll plug it in back into our theory. And you can write this down in your notebook as you're taking these down. So again, that distance was 0.65 meters, 65 centimeters. That makes sense. It's a couple feet. And 0.832 meters per second. That's the speed at that exact same time, at that distance as well. And then the other thing we're going to need to do is get the acceleration of our object, and that's just going to be the slope of the velocity versus time graph. And so you guys know how to do that. Just apply the curve fit. There it is, 0.533 meters per second, or meters per second squared. That's the acceleration. And so what we'll do from there is we'll plug all of that data into the formula that we set up. So the mass times the acceleration times the distance for the cart should equal its change in kinetic energy. So we'll check to see if that is the case. And when we do that, I'll just kind of fast forward this here. This is the left-hand side. This is the mass times acceleration times distance. And the right-hand side is down here, 1/2 times the mass times v squared. You'll notice, I'll pause it right there, that for the top I got, which is the left-hand side, I got 0.553 joules. That's the work done on the cart. And on the right-hand side, the kinetic energy down here, I got 0.547 joules, which if you just look by eye, those are pretty darn close. We'll do the percent difference. You just take one minus the other divided by the original. We'll call 0.553 the original. And when you do that, you end up with about 1.1% difference in the amount of energy, or we could say, in air quotes, that energy is lost. So the question is, where did that energy go? And we'll look at the video again and see. So think about all the places we could lose energy here. Usually in this type of situation, we're going to be losing energy in the form of heat. So for example, you've got friction in these little wheels, you've got some friction in this pulley, and possibly a tiny bit of air resistance. Consistently among my classes, we got less than 2% energy lost, which is pretty darn good. A lot of that might be coming from some uncertainty in our measurements. Anyway, the next thing we want to do is take a look at, while we've got the video pulled up here, what it looks like when we consider the work done by the hanging mass, my mass hanging off the table. It's going to fall a distance, same distance, by the way, that the cart moves. And while it does that, we can use that to calculate its work done. So the force that it exerts isn't just mass times acceleration. That's even easier to find. It's just its weight force. So its weight force times the distance it falls will be its work done. Let me show you what that looks like as you see it proceed there. So back to the actual theory. We'll call this method 2, and you'll see that in the transcript of this, the typed up version of this. So the work equals change in kinetic energy. Looks pretty similar. Let me back up. Oops. So pause it right here. This is the same place we started before. The work is just the force times the distance. Now instead of the force coming from ma times d, it's going to be the weight of the hanging mass. The right-hand side is going to look, again, very similar. So now instead of the mass of the cart, we're going to have the mass of the hanger times its acceleration due to gravity times d. And on the right-hand side, we've again got no initial kinetic. We'll have the final kinetic. I'll move it forward just a little bit. So the mass of the hanger times its acceleration of gravity, times h. Hey, look, we've got mgh on the left. That looks like our formula for potential energy. On the right, it looks like we've got our formula for kinetic energy. So in some way, we're actually dealing with conservation of energy. One thing to note, on the left-hand side, we've got the mass of the hanger. On the right, I may not write it in here, but we do have the mass of the cart. Because keep in mind, what's going on here is there's work done by the hanger on the left that's going to equal the change in kinetic energy of the cart on the right-hand side. So to summarize that, the left-hand side is just the potential energy of the cart. How much work did it take to get the hanger up to top, or up to where it started? It's going to fall a distance h, and the force it exerts will be its weight. On the right-hand side, that'll just be the change in kinetic energy of the cart. And that'll be at the end. The other piece of data that you need is that the hanging mass has a mass of 90 grams, or 0.09 kilograms. And, of course, again, the distance there, since it falls a distance that's going to be equivalent to the distance the cart moves, it's going to be the same as the distance we had just a moment ago. So 0.656, which we got, again, from the graph. So I'll kind of fast forward us through this as well. So I just plug in those numbers. That's mass times acceleration due to gravity times height. And then again, I'll give a number, 0.579 joules. That's how much potential energy the cart had at that moment. And then that will be the equal to, or close to equal to, the change in kinetic energy of the cart, which I'll show you right here is going to be 1/2 its mass times speed squared. And we end up with the same number we had above, 0.547 joules. If you look, those aren't visually as close, so we'll do the percent difference, and you get something like 5.5%, I think, is what you end up with. And so the question is, why did that number go up? I'll leave that for you to think about, and we'll have a talk about that during class. So to finish this video, what I'm going to ask you folks to do is follow this same procedure. You may want to watch this video back one more time. You're going to want to do method 1, method 2. Method 1 was where you found the work done on the cart should be equal to a change in kinetic energy. You do that by extracting some information from the graphs. For the second method, you'll do the same thing, except for you'll take the mass of the hanging cart times the distance times the acceleration of gravity, get the same thing, that'll be the potential energy, and check those numbers as well. What I'd like you to do then is submit that to Schoology. That'll be your evidence that you participated in today's e-learning day. Thanks. Let me know if you guys have any questions.